years ago, I never used the college as anything. All right. So, good. Here come the people. And let me see if I can fix the noise. Okay. All right. So we got about 10 minutes for the official start time, and I found a lot of interesting news to look at. Ransomware is really huge. This had some interesting facts. The biggest ransomware payment ever so far is $1 million. These guys tried to get $5 million, and they didn't have the money, so they turned them down and offered them $400,000, which they didn't take, and then they restored them back up. So this company in July didn't pay the ransom, but most people do pay the ransom, and insurance companies typically cover it, and insurance companies typically tell you to just pay the ransom. And my friends in the business say everybody just pays the ransom because it's much cheaper and faster. Even if you have backups, it's much cheaper and faster than restoring from backups. So that's why it's just a license to print money. I've been thinking about what to do about this, and it's actually very easy to detect suspicious activities of encrypting a lot of files. Microsoft added a feature in Windows 10 a few months ago that will detect if a folder has a lot of files changing all at once. And it seems to me like it would be easy for the cloud providers to put on some kind of system where nothing can like change all the files quickly and then delete your backups without like sending you an SMS or something. I would think if you offered some optional anti-ransomware feature in cloud providers, people would pay more money for it. Because I got cloud-based backups, but they could be nuked too. And I don't know why you could just have a backup that can't be erased until 90 days later. That would be simple enough, and people would pay the price. But anyway, I'm hoping people come up with some popular solution like that. And it seems to me like patching the cloud providers would be more efficient than trying to patch all the endpoint devices and servers at companies. But anyway, right now, everybody's pretty much a sitting duck for ransomware, and the bad guys know it, and they're just raking in the dough. So there's this Chinese app that lets you put your face on somebody else's, and as a fine French hacker that I've learned a lot from, Elliot Anderson, figured out, they are not deleting anything. Even when you delete it, it just stays on the server forever. Even when you try to block other people from seeing it, you can just go back to the URL and it's still sitting there, which is pretty common. People don't actually remove things. This was true, I think, of Instagram a few years ago and Facebook and such. So this means the data will hang around even if you wish you could delete it. So that's generally the case. If you don't know what people are doing with the data, they're typically doing something bad. So this, yeah. Well, it sounds like just a mistake to me. I think what it usually is everybody, including me, they just try to rush to get it out there fast. They connect to some random cloud provider and they don't bother with the details. I think that's how almost everybody is. In fact, I've heard one of our students that got a job at a major company is talking about the horrible mess that has to be cleaned up to create compliance. And I've heard on Pulse Security Week, they were saying the same thing. The typical enterprise has like thousands of cloud servers, Kubernetes instances, every service has thousands of endpoints, and they haven't even ever enumerated them, much less secured them. So typically when a company's in the startup phase, they're just throwing stuff together everywhere to get it working until they've got a horrible mess with like several generations of code all imperfectly patched together. And then when they try to secure it or achieve compliance, somebody has to tidy it up, and that's a huge job. Anyway, so this one.
Are they rushing because they're trying to get their VC money?
Yeah, you're trying to get some product out to sell your product to get some revenue, and if you don't do that, you'll just be gone anyway. So it is correct. The first concern is just availability. I'm just trying to make it work, and people are rushing in with feature requests and requests from your investors and stuff, and your staff is just racing to patch in what you need. And I mean, a lot of startups have no intention of ever cleaning it up. They don't turn a profit. They don't do anything. They just want to make a proof of concept and then get bought out. And then the corporation that buys them out will inherit the job of cleaning up this mess. But the ones that last have to go through their own step when they clean up the mess. And one common driver is compliance. When you have a customer that says you must meet a compliance standard, then all the compliance standards means you have to knock off this nonsense of everybody logging in as root, the server's not having proper backups, not having proper firewalls and routing controls and all over the place. You know, you have to do the work of actually being neat and organized. And you have to have version control and the same version of stuff everywhere and all that jazz. So that's pretty amazing. Trump said that Alabama was at risk from this hurricane, which all the weather people said it absolutely was not. So to make up for that, he got somebody to take a Sharpie and draw an extra line on the projection map so he could project a map which made it look like Alabama was included. This was his attempt to, it's the kind of amazing stuff, which is, it makes you wonder. Like, a lot of people are amazed at the mental fitness of Trump. I mean, he does this stupid stuff that is more than most military dictators would do, of just trying to look like he knows what he's doing in a ridiculous way, like lie when he's totally going to get caught. It is very strange. Yeah. I certainly hope he doesn't get reelected because he's awful. It would be nice. I mean, and I think the Democrats are assuming that all Biden has to do is not beat Trump and he'll win. And that might be true. That does seem to be about all Biden brings to the table is that he's not Trump, but maybe that's enough. He does. He does. Biden is a very discouraging fellow, just like Hillary was. They're running a candidate that is very unpopular, but maybe Trump is even more unpopular. It's just a very strange system we have, where it doesn't seem like we're picking the best person from either party. We're just putting up bozos and choosing the least stupid of two rotten choices. It's a very strange system. And I must say, it's no better in Britain. Britain just seems to be a bunch of complete clowns. I guess so. It's very strange. Both America and Britain, with very similar democratic systems, are just sinking in the same morass of just putting complete nuts in charge that everybody hates, that do stupid things until you throw them out, and then some other nut goes in charge, kind of like college. It's very strange. Yeah, you would think that we'd have. I thought Obama was a real leader. I thought he really knew what he was doing, and I respected him. And occasionally get guys like, but it doesn't seem to happen very often. We usually just have an idiot up there somehow. And especially lately, we've had a few people like Kennedy was really good. I respected Clinton, although he was pretty corrupt. He was effective, like Willie Brown. But there's not much to say for Trump. There's not much to say for Boris Johnson. They're just sort of like complete clowns up there, and almost everybody sees it. It's very weird. We end up with these people up there. So they got another AI that defeats Google's CAPTCHA. This has happened many times. All the previous generations of Google CAPTCHA were busted, and there were bots. This one where it has the little 3x3 thing, and it says, click all the cars, click all the street signs. As you can imagine, that's not too hard for an AI to learn, and so somebody made an AI that learned it. That thing's already pretty annoying. I have to try it 2 or 3 times often. It is actually very difficult to have something humans can do that a computer can't do, especially now in the world of AI. The whole logic of a CAPTCHA is getting more and more difficult. So we had 0 interest rate for about 10 years. Then over the last 2 years, the Fed has moved the prime rate up a little bit, up to maybe 2%, which is nowhere what it used to be. And now Greenspan says in the rest of the world, there are negative interest rates, and those are spreading to the US. And it's like mind-boggling. I mean, a 0% interest rate means it's exactly the same to pay your bills today or pay them next year. A negative interest rate means if you don't pay them until later, you have to pay less, which is kind of insane. You invest your money and it shrinks. That's both that and 0 seem like impossible numbers that make no sense. But what's that? Well, yeah, it shows. I think also the TARP, the bailout showed that money is not at all like water or physics. It's not like more of it makes the price go down and the pressure makes the price go up. It's more like just emotion. Like if people feel good, the economy's good. If people feel bad, the economy's bad. It does not obey simple physical logic at all, which is what they taught me. All the economics I learned was based on physics, and it was based on price demand and pressure putting things down and more quantity putting the price down and simple things like that. And that does not seem to be true in practice. It seems to be more like happiness. Anyway, so this one of my right-wing friends brought this up, and I went and looked it up. Trump claims that he lost 13 million votes because of Google. And this is actually from a university study, although it is highly criticized. This guy took like a total of something like 90 people, of which 23 were swing voters. And he decided to show them some Google searches and decide how many searches led to something that was negative to Trump and positive to Trump. And then he, from his basis of 23 people, he expanded that and said he lost 16 million votes for that reason. Many people are greatly complaining about this. But anyway, it's an interesting accusation. This one I'd like to check out. There's an Android app that they use for a bus pass in Britain. And this guy says the Android app just contains the private key. You can just print all the money you want on the app, and he's been doing it for years. And he published an app so everybody can just get free bus rides. That sounds like a very easy Android reverse engineering project. I feel like checking it out. It would go in my Android class. Anyway, this one I thought was amazing because they got paid for it. Starbucks had a subdomain which pointed to an Azure site. Then they took down the Azure site, but they forgot to remove it from the DNS records. So now there is a DNS record inside the Starbucks domain that goes to an unused site. So somebody can buy that domain and put up another page, and it will now be inside Starbucks. This is like the unsecured redirect page. You can now put up a link which appears to be on the Starbucks domain but isn't. So you can benefit from a trust relationship people might have to do things like steal cookies and bypass browser protections. And they paid them $2,000 for telling them about this. It's very interesting. I told a bunch of people about a similar one years ago, and most of them ignored me completely, but one of them eventually paid a few $100. These DNS problems. So Kroger and Walmart have now asked people to stop carrying guns in the store, which is like a big step. It is possible that there have finally been enough shootings that Americans are beginning to change their attitude about guns. Until now, it's always been a #1 fundamental American right to have your gun everywhere, and it doesn't matter how many people get shot, you have to have that gun, because there's a persistent myth that we're going to stop the government from hurting us by fighting back with our shotgun, as if that's going to do anything against a modern military. And there's another persistent myth that if someone robs you, you'll pull out your 6th gun and fight them off, which never happens. And other statistics are entertaining. 2 out of 3 of all the uses of all the gun deaths in America are suicide. That's what the only reason you have a gun is to shoot yourself. That's what really happens. But people imagine that they're the hero in a Western and they're going to save the world with their gun, despite all the evidence. Anyway, so yeah, they think they're going to save the country or save their family or something with that gun, even though the odds of that happening are very small. But they all imagine they're the exception. Another group like this is motorcycle riders. Almost all the motorcycle riders I know say, I'm safe, nothing will happen to me, it's perfectly fine because I'm very skilled at driving this thing. Those other people are just stupid, that's why it crashes. And I think the gun owners feel the same thing. I'm the special guy that will save the world with my gun because I'm so much more responsible with my gun than other people. Yeah, I think that's a very persistent human thing to think that you're somehow special and you can do a stupid thing and it won't hurt you because you're the special one that can get away with it. Yeah, I think, yeah. Anyway, so, all right, so we're up to Shellcode. And today's lesson is probably one of the most difficult in the whole class. We're going to look at some assembly code and we're going to see how shellcode works, and it is kind of difficult to grasp. Now, I put it all in the cloud. That's why it was updated today, because it used to be in a 32-bit local machine, but now it's in a 64-bit machine. So there's topics we'll talk about, and I have examples here all from the cloud. So system calls. So the first issue is rings of protection. There are 4. Your microprocessor comes with a whole bunch of machine language instructions that you can execute, but it also comes with operating modes. And in userland mode, which is called ring 3, you are not allowed to execute all the instructions. The instructions that would directly connect to hardware are forbidden to you. Only code running in ring 0 in kernel mode is allowed to use those instructions. So if you are in userland on your desktop, you double click something and open a program, that program cannot send any signals out the hardware. It cannot send out a network packet or put a message on the screen or anything like that. All it can do is ask the kernel to please do that for me. And the kernel is written by Microsoft, and you're just using Microsoft's call. Just like if you make a Facebook game, you have a server, but you can't put anything on someone's Facebook page directly from your server. You just have to do an API call to ask Facebook to please do things for you. That's the point of an API. And the Windows API can be used for you to do kernel-based actions like touch the hardware, and you do it with system calls. So shellcode is code written in assembly language. This is what they called an egg of your attack. After you gain some ability to execute code on the server, you then don't know what code to execute, and the typical code you want to execute is shellcode. If you can execute shellcode, that means the server will open a network connection and let you type in commands, and it'll execute any command you feed in. That's what you want typically. And that is typically what you want for remote code execution. Like we talked about this, it's pretty easy to find a denial of service attack. You see these all the time, and they're considered relatively unimportant because they just crash the server, they restart the server, block it at the firewall, and carry on. But what you want is remote code execution, where I can just send up any command I want, and now I can install malware on the server and steal the data off it and use it as an attack platform to penetrate deeper in the network, and that's usually what you want. So you're trying to get shellcode, and shellcode involves syscalls. Syscalls are what you have to do to send input or output out any device, like the network card for shellcode or the screen. So if you want to do any of these things, you have to use kernel mode commands, and therefore you have to call, you make what's called a syscall, which is how you move from userland to kernel land. So here's the protection rings. There are 4 rings in the hardware, 0, 1, 2, and 3, but 1 and 2 are never used by any modern operating system. They were provided by the hardware, but nobody found them useful. So the only thing that's used now is 0 and 3. And to be fair, in the modern world, there's called -1 and -2 are the new ones, which are hardware-assisted virtualization for virtual machines, where you can somehow simulate this whole thing in a virtual environment but those are ones that kind of break the rules. Just like in network traffic, there are VLANs that kind of break the rules between layer 2 and layer 3. Yeah?
So device drivers don't even use.
Device drivers have to be in ring 0. And that's why it's such a problem. Microsoft, you may remember Windows XP, every time your machine would crash, you'd pop up this box saying, please tell Microsoft about this problem. The reason they did that is Microsoft discovered that like 70 or 80% of all the blue screens of death are caused by non-Microsoft code. If you have a printer, you buy a cheap printer from the cheapest source available, probably from China, you get a printer, and the driver is just probably an old Windows 98 driver with just some metadata change to run it in XP or Windows 7. It doesn't really run very well, but that's what you get when you get the cheapest possible hardware. You get the cheapest driver, and that driver goes right in the kernel and runs at ring 0. It has to, and Microsoft discovered that, of course, these cheap drivers cause a lot of problems. So they started doing things as every generation of Windows moved forward. They started enforcing driver signing, where it won't let you use a driver unless it comes with a digital signature so you can verify that it hasn't been modified, because people were putting malware in drivers. And then if you buy a keyboard, you can just buy a cheap keyboard, but you can buy a keyboard that has a label on it that says designed for Windows 7, designed for Windows 10. That means they sent that driver to Microsoft and paid to get it tested and got permission to put that label on the board. And now that means that driver meets Microsoft quality standards and therefore hopefully won't crash your machine. And if you run a server operating system, they won't let you use drivers that haven't been through that test. That's why if you have a cheap machine, like a homemade one with old cheap parts you bought, and you run like Windows 7 or Windows 10 on it, then when you try to put server on it, it won't work, because the hardware that the client operating system will accept is often not accepted by the server operating system. And you can port the drivers over and override the signature enforcement stuff, but Microsoft makes that difficult because they really don't want you doing that. The fact is your server will crash and then you'll blame them and they don't want to hear it. So anyway, that's the game. Your drivers all live in kernel land. Yeah.
Is it possible to gain access to the root to virtualization?
Well, I'm not quite sure. There probably are some exploits that use hardware virtualization. I haven't heard of any, but it does seem like a fruitful area to explore. You're right, the -1 and -2 of hardware-assisted virtualization, it seems like you could do something like have a malicious bootloader that uses those to take over the machine. And there are certain VM escape attacks where they run from a virtual machine into the hardware or over to another virtual machine. There have been a few of those. And those really terrify people because, remember, all the servers are virtual machines, typically running in QEMU. Every web server and every server you get in the cloud is really a virtual machine on hardware shared with many other virtual machines. So that would be a really high value thing to do. Would be I buy a virtual machine on someplace like Amazon, and then I crawl out of my virtual machine and take over the other virtual machines on the same host. That would be awesome, and they really don't want that happening. And there have been a few exploits like that, like Spectre and Meltdown had that property, and they panicked and they accepted a 30% loss in performance to patch that right away. And DigitalOcean, one of the providers I use, they doubled everybody's RAM for the same price to compensate for it, because it was really important to them not to have that vulnerability around. Because if the customers start hacking the other customers, that's really bad for everybody. Nobody wants that.
Was that a hardware exploit?
Yes. Spectre and Meltdown was a hardware exploit. And by the way, the patch wasn't perfect. And there have been a series of further ones coming out. That's the problem. They said until you can replace the hardware with the new generation of processors that does not exist yet, you can't really patch it. So all you can do is put like a block in for the current attacks. And they will keep discovering new attacks, and you'll have to keep putting in more blocks, because you can't really patch the fundamental problem, not for years, until they come up with a whole new generation of processors that don't have this problem. And there's still, last I heard, they haven't even decided how to do that yet. They're fighting about how to make the next chip. So it's really going to be years away. Anyway, so there's protected kernel mode. This is where you go so that you can execute these things. If you try to access kernel memory from user land, you get an access exception. You're not allowed to do it. A syscall is the only thing you're allowed to do. You're allowed to execute a syscall, and then you pass it some arguments, and all you can do is execute certain functions that are provided to you. So libc is C functions that perform syscalls, like libc has printf, for example. It prints something on the screen. That, of course, involves using kernel code. So the C library, when you call it, it will ultimately make a syscall. and that's the game. So malloc allocates space on the heap, and so on. So syscall is use int 80. It's an interrupt 80. And so interrupts are signals that demand immediate attention. They're not the same as a call or a go-to. They send a hardware signal which processors are listening to. This is what happens when you press a keyboard or something. There's an interrupt. And so interrupt 80 causes the kernel to do something. And so when you do it, the CPU switches to kernel mode, and then the syscall executes, and it looks in the registers to find out what you're trying to do. So there's a syscall number is an integer in EAX, and that's a 32-bit number. And you can then have more arguments loaded in the other registers. And if for some reason there is a syscall with a lot of arguments, then one of these is a pointer to a data structure containing a whole bunch of arguments. All the things we're going to do are much simpler things that don't have very many arguments. So on Google Cloud here, I don't know if I need to do it live. I just did it in Google Cloud right before class. So this is a very simple program. You include standard library and then you just exit. It doesn't do anything except launch the program. Now, when the program launches, it has to allocate all the memory segments. So I think this is worth doing live so we can see more about how it works. So let me go here. Here's my Google Cloud machine. And I've got to go to 127, chapter 3. Okay. And so this one here is e.c. So cat e.c. All right. So this is going to include standard libraries just so I have exit. Then it's going to have a main program that does nothing except exit and come back. So I compiled this thing. And when you compile it, I compile it with 32-bit because I want to look at 32-bit code instead of 64, and static libraries, which make it easier to understand. So we can run this thing, and it will just return, and we can debug this thing and see how it works. So I can debug -q of E, and now I'm in here, and now we can look at some stuff. So I think it's, yeah, let's take a look at disassemble, and there's a few steps to do here. So let me arrange my windows as best I can to fit on the screen. Okay, so now if I disassemble, come on, disassemble main. Okay, that's the entire main in assembly code, and looks to me like maybe I should kill the intermediate light so we can see it. All right, so what you've got up here is the prologue, which prepares the stack frame by calculating a new ESP and EBP. And then you call this thing called getPCThunk, which is pretty common. And then you're going to call exit here. So it calls a C routine called exit. All right. So we now want to know what exit does, so we can disassemble exit. And exit does this stuff. It just pushes some things, and then it calls this thing called run exit handlers. So I can disassemble that and see what it does. __ run exit handlers. And that one does a bunch of junk. It's really pretty long. And it does another bunch of junk, and someplace in here, it's going to call _exit. There it is. So it does all kinds of junk and then calls something called _exit. So now if I want to see what that does, I can quit out of this one and disassemble _exit. And that one does int 80. So it goes through a bunch of intermediate steps doing all sorts of housekeeping, which we don't really care about. And then this is the active ingredient. It puts a 1 in EAX and calls int 80. So it executes syscall number 1. That's it. And the syscalls are just online in the hardware documentation for the processor. And you can see them. That's the end result, syscall 1. That is exit. And by the way, it actually did 2 syscalls. It did this here. It did FC in EAX and called this address. And then it put 1 in EAX and did it in 80. And that address, by the way, *0x80, all that jazz, if you disassemble that, that's just int 80. So I don't know why it made it so convoluted. It jumped through, jump, int 80, and then jump again in 80. But the point is, it put an FC in, which is 252. So it did syscall number 252, and then it did syscall number 1. That's what exit does. And you can see what those are if you go to online documentation. And syscall 252 is exit group killing all threads, which kills all the related threads for process, because remember, we have multi-threaded processes. So your program could have multiple threads of execution. So first you kill all the children, and then you kill the parent. That's what this is. So That's what a proper exit does. So yeah,
252. So you're saying
the 252 is, 252 is FC. So first you kill all the children, and then you kill the parent. And then you're done. That's what exit does. It kills them and then returns to the operating system. So it terminates all the processes involved in this program and then returns to the operating system. That's what happens when you click X and close a process.
So the process of getting to X involves just disassembling every exit.
Well, you disassemble, you have to find all the code it actually runs. And it turns out that in the modern operating systems, everything's not usually just in one file. This file calls another file, which calls another file, which calls another file. That's what I did. I just followed all the calls until I found the active ingredient, which was int 80. So it did a bunch of other things like setting things up, but really the end result was just syscall 252 and syscall 1.
Oh, so sorry, you were following the calls.
I was following the calls. That's all I was doing. So just so we could see it. Good. All right, so if you might want to write shellcode that does exit. Now this is of course pointless, but it's the simplest function, so we start with this way. So we want to make shellcode. Now the rule for shellcode is typically going to be put in an attack string. You'll have a bunch of A's or something, and then you'll have a shellcode in there. You'll have some nops and then a shellcode, and you jump into the nops and execute your shellcode. So shellcode should be small because typically you cannot inject a whole lot of data into an attack. Sometimes, like some of the attacks you'll be doing later, you'll have like 1,000 bytes to put things in, but frequently you can only inject a few bytes. And so that's a common problem. Therefore, to make shellcode as small as possible, you make it do the bare minimum possible, so it has no error handling. So shellcode crashes very easily. For example, if you make Metasploit shellcode that tries to make a network connection and the network is disconnected, it will just crash. It tries to make the network call, network doesn't succeed, it just crashes, doesn't pop up an error message, do anything helpful. That's normal for shellcode. Shellcode is the bare minimum code that works under good conditions and just dies otherwise. So sysexit, here's an online Linux syscall reference that shows you what they are. Let me see if I can bring that up live, link 3M. If I go to this page, and go to 3M, there it is. Here's the syscalls. And so, I can get my thing to, all right, so there they are. I wonder if they'll get bigger. Yeah, all right, so syscall 0 is restart. Here's sysexit, fork, read, write, open, close, create link, and so on. There's 338 of them. These are the syscalls. Sysexit requires EAX to be 0, and EBX is going to bring the error code back, and that's it. It doesn't use ECX or EDX. Some of the others do. So this is where you go to find out what the syscalls do. And this is the only person that normally reads this is the people that wrote your compiler, because you just write C and compile it and you let the compiler do all this. But if you want to write your own shellcode, then you do it directly to make your shellcode small and to avoid forbidden bytes like 0, which turns out to be kind of a hassle. So that's how syscall 1 works. So here's the assembly code for syscall 1. Yeah, and this is what it looks like. You have a text section, which is where the instructions are, and then you move 0 into EBX and 1 into EAX, and you call it. That's all you do. So that's all that has to happen. You can compile that. Now, if you want to compile assembly code, you use NASM. And NASM is not included in a Debian machine by default. You have to do sudo apt install NASM, but that's all you have to do. That's the assembler. Remember, we've been writing C and using GCC. But now if you want to compile assembly directly, you use NASM. That will take assembly code and turn it into object code, exit.o, and then you use GCC to turn the object code into executable code. There's a linker you can use normally, but you have to use GCC if you want to make 32-bit code on a 64-bit platform, which is what we're doing in the cloud. So here we were able to specify 32-bit assembly code, and here we specify 32-bit object code. So this will create exit shellcode, which runs and just comes back. And the point is we can see how it looks in the binary. So let's quit from here. And this is exit.asm, which I thought I had there. Yeah, exit.asm. So I can cat exit.asm. And here it is. You've got a text section that includes a main entry point. And this, the reason I put a main entry point in is so I can compile it with GCC. GCC wants to work with code that it thinks came from the C compiler, so it wants to have a main. So now I can compile that with GCC, and I end up with exit shellcode. So if I run exit shellcode, It just returns, but it doesn't crash or anything. It returns normally because it calls an exit. And if I want to see how it did that, I can use objdump -d. That will disassemble it. And I can run the exit shellcode. Okay, and when I do, I get all the code, and there are several pages of code. This is all the C stuff, setting it up. But the active ingredient is main right here. That's all that really did it. And notice the last three, exchange AX with AX, that does nothing. I don't even know why it's there. That's some kind of filler. The actual active ingredient is 10 bytes long. That's it. So what this does is it puts a 0 in EBX, a 1 in EIX, and then does an int 80. That's the active ingredient. I'm only doing the second one to execute a single-threaded process, just to make it simple. We're not doing the 252 before it that would kill the other threads. Yeah?
The results same or different if you run it on a Mac, but using a Debian machine?
If you use a virtual machine that is 32-bit, then you can compile it with different commands, and that's what my older version of the lecture had, because I had everyone use a local 32-bit machine, but now I think that's pretty much over. If you're using a local 64-bit machine, it should be the same.
Okay.
That's the big change between local and in the cloud, is everything 64-bit. And I think pretty much everything is 64-bit. That's why I really wanted to update all my classes to quit using 32-bit machines, because that's kind of over. That's anyway, so this is shellcode in 10 bytes. So if you can actually, you can eject those 10 bytes and run them on a server, you can perform an exit, which is not very exciting, but it is one way to show that you have control of the machine. All right, so you can test it in C code. So let's take a look at this. If I cat test exit shellcode, all right, what did I call it? Test exit.c, okay. All right, there are many ways to make C code that will run raw binary. And this is one way. This I kind of like because this is how I bypassed antivirus engines a lot when I was doing Python versus Norton, a project I did a few years ago. You make a data object that includes the binary you want. And these are just the 10 bytes that we got from that objdump. So these 10 bytes are executable code. It's a data object, and now you just have some C commands that cause it to take a pointer to the shellcode here and interpret it as a pointer to a function. That's what all this garbage with parentheses and stars means. It tells it to take the pointer here, which points to the start of that, and put it in another pointer, which is interpreted as the name of a function, and then execute that function. So this code tells it to run that as if it was a program. In practice, this trick causes antivirus engines to miss the code. And you'll see it in the malware analysis class. If you take obvious malware, but put it in the data section, it won't trigger. Just like if I make a web page talking about an attack, proper antivirus will not trigger on that because I'm not running the attack, I'm just talking about the attack. Yeah. Well, that's a good question. You would think heuristics would work. That's why they're there. So that's why the trick to avoid heuristics is to put in a delay. Because heuristics open malware and then try to detect to see if it's doing something bad, like opening a network socket or copying keystrokes, but they can't make you wait too long. So realistically, they can only wait a few seconds. So if you make your code take 10 seconds before doing a malicious activity, the heuristics will fail. That's one old trick. But now they're onto that, and they trap the obvious ways to do that, like sleep. They notice if you're sleeping and they're not as suspicious, but you can just do a calculation that takes a long time or otherwise waste some time or wait for something to happen like a user input or something. So these are the tricks. Anyway, so that's what this does. This is C code that runs the shell code. And you can compile it make a 32-bit code. For some reason, you have to have an executable stack. Mine is Z exec stack. I just found that out experimentally. In the book, they didn't, but when I did it on these machines, I had to add that to make it not crash. So when you compile that, you have a test exit that will run. It runs and just returns without crashing, that's all. So it's not very exciting, but it did perform the exit. So it did execute these 10 bytes as an executable program without crashing. So I'm able to feed in raw binary and execute it. And that's demonstrating what we're doing here. Now you can use strace. Strace does a stack trace. And this is actually very interesting and far more readable than I imagined. In previous classes, I just skipped to the end. Now I'm actually reading it more. It's interesting. So this test exit, you know what it does? It puts those 10 bytes in memory and then runs them. And you can see all the system calls made by that happening with strace. So strace, oops, not listening to me, strace, test exit. Oh, come on, IT. All right. All right. Maybe I got to put the // in front of it. Okay. So this is the strace. And at the end result, it calls it exit 0, which is what we wanted. But I was actually very interested to look at all this earlier stuff because now I recognize it. Remember, we talked about this before. There's a memory map. And every program has a series of memory segments, like a test section, a text section, and a data section. That's what this is all doing. You can see it. It's making a protected read, protected write map area of memory, read only, execute, protected read, map private. These are creating all those memory sections. So this is the operating system reserving sections of memory for all the pieces of your program. That's all this is doing. And we should be able to see the result by debugging it. So let's try this. GDB -Q test exit. All right, and now if I do, I don't think I can do it now. We're going to try it. Info proc map. Yeah, it's not running one. So I have to disassemble main. Okay, and so here's main. So I'm going to go down here. Doesn't really matter where I am. I'll take main plus 14 and put a breakpoint there. Break star main plus 14. Plus 14, I say. And now I'm going to run. Okay, now I hit the breakpoint. So now the program is running. Now I should be able to do an info proc map. And there it is. These are all the memory sections used by this program. And that's what all those syscalls were doing. It was reserving this memory, reserving that memory, setting permissions on all those sections. That's what it has to do. Then it finally runs the program, and the program is just exit. But it has to set up things like the stack and the heap and all these other sections. It's actually more comprehensible than I used to believe it would be. Anyway, so that's the simplest case of shellcode and how it looks in memory and how it looks in the stack. So now let's talk. Yeah, what's up?
Is it also showing a file name there too?
No, the stack trace, I don't think it shows you file names. What it shows you, I got my stack trace up here, it shows you the names of the segments. And I think some of those may have file names in it. Here's source, no recap, cache. There may be some references to the file name here, but I'm not seeing them. It's a good question. I don't see it. Anyway, all right. So now to make injectable shellcode, you see we have a problem. Here's the 10 bytes. BB0000, BH01000. Now you can't inject that stuff because the 0 terminates the string. So if you try to have an exploit that injects this, you can only inject 1 0 at the very end of a string. Everything after that will not be interpreted as part of the string and will not go into memory. So this kind of shellcode, which you create with the C compiler or with the NASM compiler, is not appropriate to get the job done. You have to get rid of those null strings. So this is why you have to understand assembly and understand binary and do it sort of by hand, because you have to make code which will run but does not have nulls in it. And a normal compiler doesn't care about that. So what you have to do is replace instructions. Move EBX0 takes a 32-bit 0 and puts it in a 32-bit register. That means there's 4 bytes of 0 in there for the 32 bits, and that's no good. So what you do instead is XOR EBX with EBX. Now that command will take every 1 in EBX, and if it finds another 1 in the second copy of EBX, it'll be 1 XOR 1, which is 0. So this will take all the bits and turn them to 0, but it does it without literally referring to the 32-bit number 0. So it ends up with the same result, but it doesn't have any zeros in it. And here's another one, move EAX1. That moves the 32-bit number 1 into EAX, and the problem with that is it has 3 bytes of 0 in it. All the higher order bytes are 0. So what you do is you go back to the legacy stuff we talked about last time, and you use the old 8-bit command to move 1 into the lower 8 bits of A. And one thing I've always wondered about is what if there happen to be non-zero bits in the higher bits, but apparently you can just not worry about that and it will be fine. In practice, it works. It would be kind of fun to write some assembly code and see if I can trick it someday by putting something in the higher order bits and then doing this command. But anyway, in practice, this results in a 0 being in the entire 32-bit A register. Yeah? XOR works because 1 XOR 1 is 0. And 0 XOR 0 is 0. So if you XOR something with itself, the result is always 0. And by the way, a lot of compilers will in fact do that because this is smaller and faster than that. So that's the game. So here's the old shellcode, did move EBX0, move EAX1. Now I'm just going to XOR EBX with EBX and move AL1. That's the difference. And that one I called exit shellcode, exit2 shellcode. So let's take a look at that. If I leave this, I can cat exit2.asm. So there it is. It uses XOR and move AL instead of move EAX. And if I look at, I compiled it so I can run it. And of course, it just exits without crashing. It does the same thing. And I can do obj dump to see what's in there. Obj dump minus D will disassemble it. So it's exit to shellcode. And it has all the boilerplate around it, but the active ingredient is here. And so you see, this is now 31 dB, B001 is put 1 in AL, and CD80 is in 80, same as before. Now it's only 6 bytes long instead of 10 bytes long. And there's no longer any zeros. This used to have a bunch of zeros in it for 0000 and 0001. Now I get the same job done with less bytes and without any forbidden characters. So that's what we need. And that's what you see here. It also has this filler junk at the end that I don't really understand, but I don't really care. All right, so now we can spawn a shell. So the point is now you probably want to do something more fun than exit. Exit is kind of pointless. That's just to prove a proof of concept that we have control of the machine. If we can execute an exit, we can execute any syscall we want by just loading the right values in the register. So we want to do a more interesting syscall like spawn a new process, which in principle we'd like to make a network connection, but that's too irritating. We're going to start by just spawning another shell. This is called a local shell. So here's the right high-level code that does what you want. You assemble it, then you analyze the assembly and rewrite the assembly code to avoid nulls, replacing instructions. That's how you do it. Then you extract the commands and you have shellcode. So if you want to create a new process on the machine, because you're injecting this code into something like, say, a web browser. There was a bunch of 0 days that came out recently. The nation of China was attacking their ethnic Muslims, the way they attacked the Tibetans a few years ago, by putting up web pages designed to attract them. And when they browsed those pages on an iPhone, they would use 0 days to take over the iPhone and steal data from them. They've been doing it for years before they got caught. And so suppose you're trying to do that. You have a web page and you're trying to spawn a new process in somebody's iPhone. Well, they're running the browser process, WebKit, and you want to spawn a new process. So you do that with either fork or execve. These are common ways to do it. Execve will replace the running process, which would cause the browser to stop and run a new process. Fork would probably be a lot better if you don't want to get caught. Then the browser will continue running, and unknown to the user, a new process has appeared. Anyway, so execve is what we're going to use here. Fork would probably be better for a real attack. So if you read execve, it tells you here, it executes the current program caused by file name, which causes the existing program to be replaced by the new program, so the existing program will not run anymore. That's execve. So you can do that in C. Here's the way it works is execve has 3 arguments. The first one points to the command to execute. The next one points to the whole array of strings. And the third one we aren't using, it's null. So anyway, it's kind of goofy. You put the same information in twice, the first element here and the first element there, but that's the way it's written. So you can compile this thing, and when you run this thing, exactly, it will just give you $1 here. It's spawned a new instance of bash. That's all it does. And the only way you can tell is it doesn't have this directory in it, because it's opening without your environment variables, without your init rc file, bash rc. That initiates bash. So that's execve. So let's take a look at that. To get out of here, I should have execve here and execve.c. So if I cat exec.c, okay, there it is. So this is the correct format, kind of screwy that it is, to execute bin.sh. Now just to show you what's going on, I could do that here. I could do /bin/sh. If you execute that, it executes the default system shell, which does not have this, it's not the bash shell, it's actually the dash shell, I think, in modern versions of Linux. And bash and dash are pretty much the same. The only difference is some of the convenient features in bash are gone, like up arrow to see all the commands and stuff. So that's all it does. It moves from bash to dash. And you can exit here and get back to bash. So like the exit we did before, this is not very valuable. It's just something to show that we have figured out how to control the machine. That's all. So you can run that thing. It's compiled to exec VE, and then it opens that shell. So you can see it's working. EXIT. All right. So now we can look at the assembly code. We can go to GDBQ and disassemble main. So let's do that. GDB, quiet, on exec VE. Okay, and now disassemble main. And here it is. And I see a chat comment coming in. Why is shell 1 even necessary? Yeah, I don't know. I've read the manual a few times. That's the structure of it. Like I say, it's kind of screwy. Instead of passing the first argument and the second argument, you pass the first argument and then an array to all the arguments, and then a null at the end for a third thing. I think the point is that way you can pass a larger number of arguments in principle, in case you want to spawn a command that has several parts. It's a little screwy, but you do have to have that there. It won't let you. I've tried to run it without shell 1. I had the same feeling when I was doing a TTF where they had a command like this, obviously based on this chapter of the book, and you really have to have it there or it won't work. I've seen some people try to do it with a null there, and for some reason it doesn't work. So it's not a very good answer, but that's what I got. Anyway, so here's the disassembled code, and what we want to see here, let's see, this one is, okay, good. What we want to see here is the part that calls execve, which is down at 59, and there it is. So here it's going to call execve, which is the C library. So before that, it has to put parameters in the registers. Remember the way, so the parameters, it had 3 parameters. Remember it had the, and so they are here. It pushes one, pushes another, and puts one in a register. Here's, so I think it's these 3 pushes. It puts a 0 on the stack, then it puts ECX on the stack, which is 10 away from EBB, pointing to a string, which is /bin/sh, and then it pushes another parameter on the rack, EDX, which points to something else. Those are the 3 pushes to put the 3 parameters on the stack, and then you call the function. Remember, this is how it works. You first push all the parameters on the stack, then you call a C function. The C function looks on the stack to find the parameters. And that logic is what leads to a whole series of vulnerabilities, because when you call this function, it really has no way to tell whether you really put parameters on a stack properly. Other languages would be more careful and check that you had done that. C never checks anything. It just runs the program, goes on the stack, assumes that whatever there is what it needs and uses it, even if it's obviously blatantly stupid. That's the fundamental principle of C, is that it should not waste time trying to argue with you. It should assume that you're an expert and do whatever you told it to do as efficiently as possible. And it's your duty to be smart. And the idea is code will run really fast and be really clean if you are genius. But if you're sloppy, you'll make a disaster. And in practice, that's what the end result is for most C programmers. They create this stuff and it turns out they're making mistakes. But it was written not for the average programmer, but for the really super duper programmer that certainly understands this stuff and wants to make beautiful, fast code. Anyway, so if you disassemble this thing, you see that? All right. And by the way, it eventually goes down to an int 80. So execve is here. And let's follow that a little bit more. So here it's calling execve. And if I disassemble the execve, so we saw it loads some stuff in the parameters, then it calls execve. So let's do the same thing we did before. Let's disassemble execve. Okay, execve brings in the parameters, moves them around, puts the parameters on the new stack in the new stack frame, and then it calls this address again, which might look familiar. We've seen this before. If I go there, disassemble that address, that's int 80. So ultimately, it's going to perform an int 80, and it's going to do it. It's going to execute syscall B, which is 11. So that's syscall number 11. And I think I've still got the page open here. So syscall 11 will be on the next page. All right. Syscall 11 is sysexecve. So because you're spawning a new process, that has to be done from kernel mode, and you do it with the syscall. So all we're doing is laying up the arguments and calling a syscall. And by the way, this one has a bunch of arguments. AXE, BXE, CXE, DX, and ESI, and all that jazz, because it has to pass those 3 arguments in. So it uses a bunch of registers to point to the various parameters here. All right, so that's all. We're just seeing what's happening inside the machine. All right, and so here's, there are a few versions of syscall, by the way. There's int 80, and there's also this weird thing, call *%GS:10. There's different instructions that amount to syscalls. Anyway, in our current Debian, we're actually getting it. So anyway, here's final assembly code with all the goodies. I'm not going through all the details. Here's assembly code that actually does something useful. It's going to pop junk to XOR, move on. This is assembly code from the book, and this will run bin/sh. It's complete assembly code that will do it. So you can run that thing in C, and it opens this local prompt with a $, the same as before. But this is real assembly code designed to dodge all the zeros. So it's written in a way to dodge all the zeros. And you can see that here, it moves a byte instead of into AL, that's a single move. It does XOR EAX to EAX instead of using a 0. This is what assembly code looks like when you have rewritten it to avoid all references to null. So it's kind of painful, but that's how you do it. All right.
What does null do?
Null terminates a string. So if you're sending a string to C code, that's not always the case. I've written some projects you'll do where I actually take the data in something like hex, so you can use nulls. But typically in a normal vulnerability situation, you're feeding up something like a URL or a file name or a password, and a null is not allowed. A null terminates the string. Yeah. You want to put in something like a username that has 500 characters, but if it had a null in the 100th character, that would be interpreted as the end of it, and it would never see the rest. So you have to avoid nulls, and in practice, if you're going through web forms, you often have to avoid tabs, carriage returns, line feeds, and similar other characters, a series of bad characters you have to dodge, but the one you almost always have to dodge is a null. So even this kind of code, which doesn't have any nulls, might still fail for other reasons in a real exploit, and you might have to avoid more. And we'll be using Metasploit to make our shellcode, and in Metasploit you can use the -b flag to just list a bunch of bytes you're not allowed to use. And it will generate shellcode that doesn't use any of those bytes. But you do have to go through a sort of irritating, tedious process of testing all the bytes to make sure they work. All right, so I got some cahoots about that, and then I'll take a look at the project. We'll take a break before we do that, but let's start with the cahoots. I should have a page of cahoots around here someplace. There they are. Good. All right, so it's this chapter 3. There we go. And it's all ready to go, so good. And I even have a place to put the answers. All right. All right, so we got about 8 in the room and about 7 online, so I guess we should get up to maybe 10 cahooters or more. Oh, there they come. Cahooters. All right. I'll wait a few more seconds to see if we're going to get more, but this would be a typical turnout. Anybody in the room still going? You coming in? Okay, good. I'll wait. We're not in a hurry. You can. You come. Okay, fair enough. Okay, let's go. All right. So, all right. So what item converts executable code into assembly language? Okay, that's objdump. That takes compiled code and turns it back into assembly language. Objdump -d is what we used to do that a few times. NASM does the opposite. It takes assembly language and makes it executable. It's a compiler. All right. So what item will list all the system calls when a program is run? That strace, which I think is system trace, I called it stack trace by accident earlier, that shows all the system calls. And as you can see, even when you're doing something incredibly simple like exit, it has about a dozen calls before that just to make all those memory segments that it uses. Just the necessary overhead to run any program. There's a bunch of junk it has to do. All right. So what takes you from user mode to kernel mode? A syscall. which you do with int 80, but that's called a syscall. That calls the system, which is the kernel. All right. And which item converts assembly code into object code? That's NASM. NASM takes assembly code and turns it into object code. Then you have to link it with libraries to turn it into executable code. And we did that with GCC, but on a 32-bit system directly, we could have used LD, a linker. And GCC typically does them both, but there are actually two steps. First, you make object code, which is binary, but it's not connected to libraries. Then you link it, connect it to the necessary libraries, and then it's ready to run. All right. And so what instruction should you use instead of move AX0 in shellcode? Okay, you got to use XOR, otherwise you have a bunch of zeros in there. And I saw a chat message coming through, and here it is. Okay, path name must be either binary executable or a script starting with this line. So in our case, the array pointing to the bash shell. Why a shell? This is why the shell is necessary. Oh, good. Okay, yep, that's right. The documentation says you have to have it there. That's as far as I got. But yeah, you do have to have it there. Good, all right. So that's that one. And there's the next one. Okay, what do you do instead of move AX1 in shellcode? You have to move one into the low byte. If you move one into the high byte, you're going to end up with 256 instead of 1. So you got to move AL1. That'll put a 1 in the low byte, and that will end up in a 32-bit 1. All right, so here are the winners of this. A couple of names that look real. Tan Lai. If I can only get my capitalization under control. Okay, and Ken Tan. And your Kahoot. Okay, good. Ed, right? Ed F, right? Good. Okay, good. Good. All right, so I know who the winners are. And all right, so it's 6:56. Let's take a break until 7:05. And I will stop the recording and make a separate recording of that. I'll demonstrate some of the projects.